Okay, so this topic is a combination of capacitors in series and in parallel. So we have to first understand what does it means to be in series. We'll first do series, capacitors in series. So what does it means? Now, if you have capacitor in the previous video, we have done the capacitors pictorial symbol looks like this. So this is the two plates of the capacitor. And let's say you have three such capacitors stacked up like this. And one end of this capacitor is connected to the positive terminal of the cell, and other end of this third capacitor is connected to the negative terminal of the cell. Now, because this is a positive terminal, so the positive terminal will give positive charge to here. That means this plate will develop positive charge. And as because this is a negative terminal, so the negative terminal of the cell will give negative charge to here. Now, because of induction, electrostatic induction, I hope you remember, because of the induction, you see these two plates are not connected, or these two also, these plates are not connected to the cell. Are they connected to the cell? No, they are not connected to the cell. As because they are not connected to the cell, they are not going to get charge directly from the cell itself, because they are not connected to the cell. But because of induction, this positive charge will induce negative charge on this plate. And as because negative charge is concentrated here, an equivalent positive charge will concentrate here. Because these two plates happen to be isolated, they are not connected to the cell. So if negative concentrate here, positive will concentrate here. Again, if there is a positive charge on this plate, so due to induction, there will be a negative charge on this plate and then a positive here. So look very closely that these charges, the one in the blue, they are induced on the plate. These charges are not from the cell. The cell is effectively giving the charge positive and negative. Only these two charges the cell is giving directly to the system of capacitor. And these charges are developed due to the induction. This is what's called the capacitor in series. Let's read the definition. If the negative plate of one capacitor is connected to the positive plate of second. So as you can see, this is negative plate of one capacitor is connected to the positive plate of second, and the negative of the second to the positive of the third. Again, negative of the second to positive of the third. So then this is said to be in series. The capacitor is said to be in series. So this is a series setup. Okay, capacitors in series. I have drawn three capacitors. You can draw more. Now, consider the charge on the capacitor. Consider the charge Q on the capacitor. So what is the charge on the capacitor? If we consider this capacitor, it has a charge Q. But because the second capacitor, this charge has been developed due to the induction. These are induced charges. That means whatever be the charge on this positive Q is, the same negative Q will develop here. And the same positive Q will develop here. Same negative Q will develop here. And the same positive Q will develop here. If the cell has given positive Q charge to this plate, that means the cell must have given the negative Q charge to this plate. So negative Q will develop here. Effectively, you will see that each capacitor has the same charge. All these capacitor has same charge, Q, Q, Q. But think about the cell. how much of charge cell has given to this system. The cell has also given the same charge, that is Q. As I told you before, that these charges are not supplied by the cell. These are induced charges on the plate. Cell has only supplied these two charges. And with respect to the cell has given a charge of Q, only Q to the system. Okay. If you don't understand this, go back and see this again. This is very crucial, or else you will not understand anything further. So this is very crucial for the series capacitance to understand that each capacitor has same charge. All the capacitors connected here will have same charge. But don't think that all the charges has been supplied by the cell. The cell is only supplying these two charges at the end. The other charges are induced. Now, each capacitor will have certain capacitance, C1, C2, C3. In the previous topic, we have done that the capacitance of the parallel plate capacitor is epsilon naught A by D. So by this logic, you can deduce that the capacitance C1, C2, C3 may be different. They might have a different area or different distance between the plate. So the C1, C2, C3 can be different values. We also know that Q is equal to CV. That means V, potential drop, a potential difference between the plate of the capacitor here. The potential difference between the plate of this capacitor is V1, which is equal to C1. V1 is equal to Q by C. But because I'm calculating V1, so I'm going to take this as C1. Similarly, there will be a potential drop across the second capacitor as well. And this potential drop across the second capacitor will be Q, charge on the second capacitor, divided by the capacitance. The third capacitor will have the same thing, that is the potential drop across the third capacitance will be Q by C3. So eventually you will have the three potential drop across these individual capacitors. As you can see, this is V1, this can be V2, and this is V3. C1, C2, C3. So what do we have? We have three different capacitors, C1, C2, C3. As because they are connected in series, so the charge upon them will be same. And this is true for all kind of series connections. Whenever the capacitors are connected in series, the charges in all of them are same. As because the charge in all of them would be same, so they would develop different potentials V1, V2, and V3. Now, as you know that potential V is effectively the potential energy. Potential is basically an energy. It's a unit. It's a scalar value, unit of energy. So the potential developed by this each capacitor V1, V2, and V3 must be given by the cell. That means with respect to the cell potential, the potential of the cell will be is equal to V1 plus V2 plus V3. And why V1 plus V2 plus V3? Because the cell is the source of energy in this circuit. Cell is supplying the charge and it is the source of energy in the circuit. V1, V2, V3 is the potential or the energy difference or the potential drop across each capacitor. So the sum of all three, V1 plus V2 plus V3, must be is equal to the energy that is provided by the cell, that is the potential difference of the cell itself. Now, think about the cell. Think that cell, what is the cell doing in this circuit? Cell is only supplying charge to these two plates. And with respect to the cell has supplied Q charge. Cell has supplied Q charge to the circuit. Now, cell does not care if there is one capacitor, two capacitor, or three or n numbers of capacitor. With respect to the the cell is going to consider all the three capacitors, as a system, and that system will have a equivalent capacitance, C equivalent, CEQ. So this equivalent capacitance is with respect to the cell. You see, the cell doesn't care it is C1, C2, C3, C4, C5, whatever it is. Cell only knows that it has supplied Q charge to the circuit, and whatever be the capacitance all combined with respect to the cell is going to consider them all equivalent as one. So with respect to the cell has supplied Q charge, and the cell is considering that all the capacitors would combine to make a C equivalent CEQ. V1, V2, and V3 we have found out as Q1 by C, Q2 by C, Q1 by C, Q by C1, Q by C2, Q by C3. So this would become Q by C1 plus Q by C2 plus Q by C3. You can take this Q out, and then your equivalent capacitance, the equivalent capacitance of three capacitors connected in series would become 1 by C1 plus 1 by C2 plus 1 by C3. It is a very simple derivation, standard PU plus CBSE derivation. बहुत ही simple है, very simple. And few points you need to always remember for this derivation is the reciprocal of equivalent capacitance is equal to the sum of reciprocal of individual capacitance. So as you can see, this is a reciprocal of the equivalent capacitance is the sum of the reciprocal of individual capacitance. Sum of reciprocal of individual capacitance. The equivalent capacitance is smaller than the smallest individual capacitance. This is an important point. So for example, let's say the three capacitors here, C1, C2, and C3 are 3 mu F, 5 mu F, and 8 mu F. So the smallest capacitor here is 3 mu F. So equivalent capacitance value will be less than this value. Less than this value. What is it this given? You see, read this again. The equivalent capacitor is smaller than the smallest individual capacitance. So here this 3 mu F is the smallest individual capacitance, and the equivalent capacitance is going to be less than this. Charge on each capacitor is same, that we have understood. Be very clear about the charge on all the capacitors in series is same, but don't confuse that all the charges on all the plates of the capacitor is supplied by the cell. Cell is not supplying all the charge on all the capacitors plate. Cell is only supplying the charge on these two end plates. The other charges on these capacitors due to induced charge. And the last point is that the potential difference across any capacitor is inversely proportional to its capacitance. That is very simple. V is equal to Q by C. That is, these are inversely proportional. Now the next topic is capacitors in parallel. So first let us draw and see how a parallel plate capacitor setup looks like. So let's say you have three capacitors. Let's make it small. It really doesn't matter how you make it, I mean how you draw it. Some people choose to draw it like this. This is also correct. You can draw it like this, or you can draw it in any way. Okay, you can draw it like this, or you can draw it like that. All are same. So here we have three capacitors and they are in parallel, and the the point at which these capacitors are joined, this point is then connected to the positive terminal, and the other point here is connected to the negative terminal. Now look at this figure carefully. Each plate of the capacitor is effectively joined with the cell. They are all in contact with the cell itself. See, in series, this was not the case. In series, each plate was not, all the plates were not joined with the cell. The plates of the capacitor were joined with itself, with each other. This plate is joined with this one, and this plate is joined with this one. They were not connected to the cell. But in parallel, in the parallel circuit, look closely, each plate, this plate is also joined with the positive terminal. This is also joined with the positive terminal. This is also joined with the positive terminal. All the plates are individually connected to the cell. Because all the plates are individually connected to the cell, so whatever the charge which comes out from this positive terminal, these charges goes to all the plates. So the positive terminal provide the positive charge on all these three plates, and the negative terminal provide the negative charge on these three plates. So you can very well conclude that whatever the charge which is coming out from the cell, if I consider that there is a Q charge which is coming out from the cell, this Q charge must be is equal to the charge which individual these plates have. So the Q, that is charge that is coming out from the cell, must be is equal to Q1 plus Q2 plus Q3. So when the positive terminal of all the capacitor are connected to one common point, as in you see, this is one common point, and the negative plate to another common point, as this is another common point, the capacitors are said to be connected in parallel. The individual charge of the capacitor, Q1, Q2, Q3, they all combine, and the sum of all these three, Q1 plus Q2 plus Q3, will be the total cell, the total charge that is coming out from the cell. These three capacitors will have their individual capacitance, C1, C2, C3. Now, because these capacitors, look closely, these capacitors are individually connected to the cell, they will have the same potential difference, as that of the cell. All the three capacitors will have the same potential difference because they are individually connected to the cell. So they will have the same potential difference of the cell. Whenever you connect a device directly to a power source or a cell, that device will always have the potential difference of the power source it is connected to. So these capacitors are connected to this cell and they have the same potential. Now, with respect to the cell, the Q charge that is given by the cell can be written as Q is equal to CV. The C here is the equivalent capacitance. Again, the same story. The cell doesn't care how many capacitors are there. With respect to the cell is only considering that all the capacitors are combined and they are behaving collectively as an equivalent capacitance. So with respect to the cell, the all three would combine to make one equivalent capacitance, and that is what the cell is going to consider the capacitance or the capacitance of this entire circuit. So Q is equal to CV, C equivalent capacitance into V. V is the potential of the cell. C equivalent is equal to C equivalent into V. Now Q1. So what is the C? Q1 is equal to the capacitance 1 into the potential difference V. Capacitance 1 into the potential difference V. Similarly, Q2 also is equal to the same capacitance 2 into the potential difference and the capacitance 3 into the potential difference, the same. So you'll have C2V plus C3V. You can take V common from both sides and take it out. And in that case, your equivalent capacitance will simply become C1 plus C2 plus C3. Very, very simple. So when the capacitors are in parallel, the equivalent capacitance is simply the sum of the individual capacitance. When the capacitors are in parallel, the equivalent capacitance is equal to the sum of the individual capacitance. As because the equivalent capacitance is the sum, that means the equivalent capacitance is larger than the largest individual capacitance. Obviously, because you're adding them up. Potential difference across each capacitor is same. Again, why same? Because they are all connected to the cell individually, so they will have the same potential difference as that of cell. The charge on each capacitor is proportional to its capacitance, because Q is equal to charge Q is equal to CV, and if V, that is potential, is same for all of them, that means the charge would depend upon the value C. That is why the charge on each capacitor is proportional to the capacitance. So what have we understood here? That when you connect a cell, when you connect these capacitors in series, when you connect them in series, the charge on individual capacitors remains same. In series, the charges are same. Potential is different. Charges are same. Potential is different. Do not forget this. And in parallel, potential is same and charges are different. We'll have different charges. Q1, Q2, Q3, the charges would be different. That depends upon the individual capacitance, but the potential drop is same. Potential drop is same.